Planet time, planetary momentums. So what we're doing here is we're going to be looking at angular momentums again, but in a kind of strange way. We're going to look at them for planetary orbits. So, we, in our solar system, our sun, the sun, is a star in the center, and then we've got our planets going around, for the most part, in near perfect circles. Okay? These circles aren't exactly perfect. They're actually ellipses. But for the most part, the planets going around the solar system are going in near perfect circles. But what if you didn't have a near perfect circle? What if things got a little bit weird? What if you had something that was more akin to this, an ellipse? Which is technically what our planets are doing, but just not exaggerated like this. Maybe Pluto, but that's about it. But let's say you did have something like a comet that had a huge ellipse like this, right? One of the most famous comets is Halley's Comet. And because of this, there will be some spot where it will be very close to our sun. Here, let's just do this. There will be a spot on this orbital path in green that's very close to our sun. And for our sun, we call this a perihelion. But for just a general body, you can call it a periapsis. Really, let's just think about the word peri being very close here, or the closest. And on the far side of things, we could be way out here. For our sun, this would be like an aphelion, but in general, we could call this an apo or an apoapsis, or just apo meaning very far away. Okay? Now, if you kind of think about this, if our planet is going around here, we can kind of get the idea that, if we're very far out and then we start falling in towards the planet, we should be speeding up and speeding up and speeding up and speeding up. And then maybe we're still speeding up. I don't know what's going on over here. But as we begin to fall away from the planet, we're like kind of jumping away from it, we'd be slowing down here until we get out to this point where it's like our maximum height, where we've kind of like just, paused up for a second, and then we start falling and speeding up. This point here, our perihelion, our periapsis, this will be our absolute fastest point. It is the closest approach to our object. It is the fastest point. And therefore, our apoapsis, or aphelion for our star, this is going to be the slowest point. Now, normally when we think of things moving on in a circular or kind of a rotational motion, we normally think about things in terms of omega, because omega is radians per second. It's some angle measure per second. But this radian right here, it kind of gets a little weird in thinking about, a planet kind of going around like this, because if our planet is moving from like here to here in some amount of time, we could find the average omega, the average angular velocity, but that's an angle like that. When we're very, very far away, how do we think about these angles? Because we're not on a circle anymore. Like we're on an ellipse, and that kind of gets a little weird, doesn't it? So because of this, maybe thinking about an angular velocity as omega may not always be the best or easiest thing to think about. Maybe it's a little easier thinking about just what is the tangential velocity or the linear velocity in these directions. And remember, these tangential components have to make tangent lines to this ellipse. So for our perihelion and our aphelion, or our peri and ap positions, these are coming in this direction. But if you were like, hey, my planet's right here, that velocity would be kind of going out like this. And if you were, right here, your velocity would be going like that. It's tangent to this kind of loop. Now, how could you figure out what that velocity at para whatever and at your apo positions are? How could you find these velocities here? How could you find how fast you're actually moving? Well, even though we're not using an angular velocity here, what we can do is use a conservation of angular momentum in order to solve this. And if we recall, angular momentum in the conservation of it states that an initial moment of inertia multiplied by initial angular velocity equals a final moment of inertia times a final angular velocity. And there are a few things that we need to recall in order to use this. The first is we need to recall that we can write omega, an angular term, in linear dimensions by saying that it is a linear velocity divided by some radial position. Where are you? And in our case here, we actually have two different radial positions. We have a distance to perihelion, RP, and much, much further away, we've got a distance to the aphelion, or the apoapsis, which is RA. So we actually have two different R's here in order to describe this. The other thing we have to remember is that for these planets or these celestial bodies going around something, we can think of them as a point mass. Yes, I realize that the Earth in a comet is not existing on a tiny point in space, but these objects are normally so much smaller than what they're orbiting around, like the sun, that they might as well be considered a point mass. We really don't need to worry about any strange effects of having a distributed body system. And because of this, the moment of inertia of a point mass is just equal to mr squared. Well, remember, this r here could be the r of the periapsis or the apoapsis point. So that r could change as well. Well, what this means, if we go down here, we try plugging some stuff in to this equation in blue, we'll quickly see that the mass of our comet or planet or whatever times the, and we'll do this for the perihelion first, the close point. So the peri point squared times the angular velocity at the peri equals m times the radius of the apoapsis squared times this angular velocity at the apoapsis. We quickly see that the mass is the mass of the moving object, and the mass of the moving object doesn't actually matter. It doesn't matter if it's a planet, doesn't matter if it's a comet, doesn't matter if it's you, doesn't matter if it is a burrito. Mass doesn't matter, which is kind of a neat thing. The second thing we'll do here is let's get rid of these omegas and use something a little nicer here. So we're going to have the radius of the periapsis squared times the linear velocity at the periapsis over the radius of the periapsis equals the radius of the apoapsis squared times the velocity of the apoapsis over the radius of the apoapsis. And what we quickly see from that is one of these radii divides out. What this allows us to do now is we can easily write this as just the radius of perihelion times the velocity at perihelion is equal to the radius of your aphelion or apoapsis, if you're orbiting something that's not a star, times the velocity of apoapsis. Or if we'd like to write this as a series of ratios, we could say that the velocity of periapsis over the velocity of apoapsis equals the radius of apoapsis over the radius of perihelion. So if you know just how far away your object is going to be at the farthest point and the closest point, and you know just one of the velocities, you can find the other one, which is a pretty cool thing to do. It tells you a lot of information about kind of how planets are moving and how they're speeding up and their closest and farthest approaches just with this method. This also tells you that the perihelion has to be the fastest, because when we look at this here, if we wanted to solve for the velocity at perihelion, that'd be RA over RP times the velocity at the apopoint. A, the radius to A, is always larger than P. By the way we define them, looking right up here into our picture, A is larger than P, which means that this number here is something greater than 1, which means you're multiplying the velocity by a number greater than 1, so this has to be larger. So by default, whatever it is, while this is true, it's going to be greater than whatever that is. So, that's a further way you can kind of prove that to yourself. But kind of a cool thing there. If we had something like Kerbal Space Program, which we might load up in a little bit when we start doing our space section, we can actually look at this and we can actually, calculate if things are activating correctly and what's going on there. So it's kind of a neat thing with angular momentum to figure out, how fast you're going to be going. So Take it easy.